If f of x is 100 times 1.25 to the x, what would the graph look like? Well, you can plot points, but one way to think of it is to think of the percent rate of change. So this function is increasing by 25% per unit of x. 25% is 1/4. So at time 0, we have 100. After 1 year, well, we add 1/4 of 100, so you can visualize adding 1/4. And now the value is 125. The next year, you have 125, but you add 1/4 of that. So you're not adding the same amount, you're adding the same percent, but it's a percent of a larger amount. So after 2 years, the value is 156.25. We've added 1/4 of the previous amount. And then after 3 years, well, you have the 156.25, but then you're adding 1/4 of that. Which is 195.31. And then after the 4th year, you're adding 1/4 of this amount. You can visualize 1/4. And you can see that the graph is concave up, increasing and concave up. What happens when x is negative? When x is negative, the y value gets smaller and smaller. It gets closer and closer to 0. And the graph has what we call a horizontal asymptote. Of y equals 0, because it's getting closer and closer to the y value, 0. Asymptote means it's never equal to 0. It just gets closer and closer to 0. Let's look at a decreasing exponential function. The initial value here is 64, and this function decreases by 50% per unit of x. So when x is equal to 0, we have 64. After 1 year, we lose half of the value. After another year, we lose half of the value again. Every year, the value decreases by half. So this is a decreasing function, concave up. And again, the y value gets closer and closer to 0. So this function also has a horizontal asymptote of y equals 0. What happens when x is negative? Well, you get bigger and bigger values of y. If we were to compare the graphs of two exponential functions, f of x and g of x, you can see from the base that f of x increases by 20% per unit of x. G of x increases by 40% per unit of x. So g of x is increasing faster. They have the same initial value, so they have the same y-intercept, but this one that is increasing faster is g of x. Both graphs have a horizontal asymptote. Y equals 0. If we look at the graph of two decreasing exponential functions with the same initial value, we can see from the base of f of x that f of x is decreasing by 20% per unit of x. G of x is decreasing by 30% per unit of x. So g of x is decreasing faster. That means this graph is g of x. This one is f of x. And again, they both have a horizontal asymptote. Of 0. So for the function f of x equals a times b to the x, if a is positive and b is greater than 1, we have this increasing concave up function. Well, if you multiplied a by -1, you would flip the graph over the x-axis. So this is the graph if a is negative, but b is greater than 1. If a is positive and b is less than 1, this would be your function. If you multiplied a by -1, you would reflect the graph over the x-axis. So this graph is what you get if a is negative and b is less than 1. So if your initial value is positive, that's your y-intercept, b is less than 1, you get a decreasing concave up function with a horizontal asymptote of 0. If you were to add c, a positive constant, that would shift the entire graph up c units. So instead of a horizontal asymptote of 0, you would get a horizontal asymptote of y equals c. Then your initial value also moves up by c. So this initial value is c plus a. You would use a graph like that to describe something like Newton's law of heating or cooling. The rate at which an object heats up or cools down is proportional to the difference between the object and its ambient temperature. So if you wanted to cool something off, it would cool off faster in the freezer than it would on your table. If you take a hot potato out of the oven and leave it in a room whose temperature is 70 degrees, it makes sense that the coldest the potato will get is 70 degrees. So we'll have a horizontal asymptote equal to 70. You can use Newton's law of cooling to decide what the graph will look like. Will it be concave down or concave up? Well, think about it. The closer the potato temperature gets to the room, the slower the cooling becomes. So obviously, this graph will be concave up. Because the cooling slows down as the temperature approaches room temperature. So for this function, because the horizontal asymptote is not 0, I know that C will be 70. You might think that A would be 350, but A is this quantity. So 70 plus 350 is the initial value. So that means A is 280. This is a decreasing function. So I know that B is going to be less than 1. I would need one more data point to find B. We'll do that in part 3. If you were to take a room temperature potato and put it into a hot oven, what would the graph look like? Well, the temperature is going to increase. The hottest the potato will get is 350 degrees. Let's use Newton's law of heating or cooling to decide if it's concave up or concave down. The closer the temperature of the potato gets to the temperature of the room, the slower it heats up. So you can see that it'll be concave down because the potato is heating up fast at first. As it gets closer to the temperature of the oven, it slows down. So this graph will have a horizontal asymptote of y equals 350. The horizontal asymptote is 350. That means that C is 350. If I want my initial value to be 70, I need my A to be negative 280. if you think about this being negative, reflecting it across the x-axis, it's really a decreasing function that's been reflected. So b is going to be less than 1. Again, we would need another data point to calculate b precisely. We'll do that in part 3.